Assalamu alaikum. Today we shall talk about a real system, a hydrogen atom. This is a two-body system. We aim to solve the Schrodinger equation and get the wave function for the hydrogen atom. Today we'll talk about up to the change of variables. Then in the next video, we'll talk about the solution of the Schrodinger equation. So let's start. As you know, hydrogen atom has two particles, the proton and electron. This is a very crude model of the hydrogen atom. At the center, this is a proton, and the electron is moving around the proton. So for the positions and momentum, let's assume for electron, the position is R1, and for the proton, the position is R2. While for electron, the momentum is P1, and for the proton, the momentum is P2. So we are using the subscript 1 for electron and the subscript 2 for proton. These R and P's are a vector, so they are all in 3D. Okay, now the components of this position and momentum satisfy the commutator, canonical commutator, that is we have learned previously. X hat do not commute with P hat, so Px hat, and this is equals I squared. But X hat commutes with Py or Pz, and that is equal to 0. This is what is written here. So I equals here I, and both j would be equals 1, 2, 3. Then for the first component of R1 would be x1. That is, I have written here like R1I. So this should be equal to this one, x1. And similarly, P1j would be P1x. And from here we can see that when I and j are same, the delta function, this gives 1. So that is delta ij is equals to 1 when I equals j, and equals 0 when I is not equals j. So we see from here that whenever they are of same component, there is the x component from R and x component from P, they do not commute. But if you take x component from R and the y component or z component from P, they commute and gives 0. This is same as for electron and also same for proton. And also one important thing, if we take any component of R1 and any component of P2, whatever I and j are, this is always equal to 0. And similarly, for if you take the commutation with R2, any component of R2 with any component of P1, the result is 0. Okay, now for the hydrogen atom or any hydrogen-like atom like helium plus or lithium 2 plus, they all have one proton at the center and one electron. And the interaction between the electron and proton is Coulombic. So if we assume that the electron have -e charge and the nucleus have Ze charge, for hydrogen Z equals 1, but for helium Z equals 2, for lithium Z equals 3. So that's why we are saying hydrogenic atom or hydrogen-like atom. The nucleus has Ze charge and there is one electron with -e charge. So the potential, there is the Coulombic potential that only depends on the distance between the electron and the proton and the nucleus. So that is given with this formula, -1/4 pi epsilon naught Ze square by distance between R1 and R2. Now this is a central potential because the potential only depends on the separation between them. It doesn't depend what is the value of R, what is the value of R1 and R2. It only depends on the magnitude of the separation of these two. So that's why this is called the central potential. Now, if we write the Schrodinger equation for this system, that would be like this. This is the kinetic energy for the electron. Remember, we are using subscript 1 for electron. And this is the kinetic energy term for the proton. And this is the potential between electron and proton. And the psi R1, R2 is the Schrodinger equation. E total is the total energy. Here M1 is the mass of the electron and M2 is the mass of the nucleus. So for hydrogen atom, this will be the mass of proton because hydrogen atom nucleus has only one proton. And also the Nabla square is actually this d square by dx square plus d square by dy square and d square by dz square. The subscript is 1 and 2, 1 for electron and 2 for proton. This is already, we know it. Okay, now our aim is to solve this Schrodinger equation to get the wave function psi. Now, for electron and for the hydrogenic atom or hydrogen-like atom, we assume that the electron position is R1 and proton position is R2. So we have a wave function like this. And the wave function depends both R1 and R2. To normalize the wave function, we have to integrate both over R1 and R2 in all three components. And that should give us 1. Here, psi star psi is the probability density. Now, we know from the experience that whenever we have a system like this, when a heavy mass is at the center and another particle is rotating around the center. So we know that proton is about 2000 times heavier than electron. So we can, from the experience of the classical mechanics, we can say this is a center of mass system. So we aim to change the variable from R1, R2 to for a center of mass system. For that, we write a relative distance or relative coordinate R that equals R1 minus R2, and we write another vector. This is the position vector of the center of mass, and that is like this way. Now we want to change the wave function psi R1, R2 in terms of these new variables. So for that, let's take the derivative of psi with x1, because R1 have three components, x1, y1, and z1. And if we do so, we have dx by dx1. This x is the x component of the capital R, and this small x is the x component of this R, the distance, relative distance between electron and proton. So we write d psi by dx1 equals dx by dx1, and d psi by dx, similarly dx by dx1 and dx by d psi by dx. Now, from here, we have R equals R1 minus R2. So if we take the x component from here, the x will be x1 minus x2. And from here also, if we take x, it would be m1 x1 plus m2 x2 divided by m1 plus m2. Now, if we take the derivative from here for this x, small x, dx by dx1, that is just equal to 1. And from here, if we take dx by dx1, it will give us m1 divided by m1 plus m2, because dx2 by dx1 is 0, x2 doesn't depend on x. So with these values, we have mu by m2. So this is another change of variable, because we had here m1 divided by m1 plus m2. So let's write it like 1 by m2, m1 m2 divided by m1 plus m2 is getting, let me write it here. So we had like this, dx by dx1 equals m1 plus m2 x1. Let me check. Yes, it's fine. So we can write it like 1 by m2 m1 m2 divided by m1 plus m2x. We don't have anything else actually. This is 1 because we took the derivative. So this is, we can write 1 by m2 into mu, where 1 by mu equals 1 by m1 plus 1 by m2. So with that, we have like this mu over m2. And this is also written, we write here 1 by mu equals 1 by m1 plus 1 by m2. So this is what we have. Okay, now if we see that here we took the derivative d psi by dx1, we came up with mu by m2 d psi by dx and plus d psi by d small x. This is the component of the relative motion. Remember here. If we write in terms of nabla, so we will have from here nabla 1 psi equals mu by m2. This is nabla in terms of capital R psi, plus we will have nabla in terms of small r psi. This is what we have written here. We dropped the this r subscript because this is no more required. Usually when we write nabla, that is for small r. So we dropped it here. Now this is for psi 1. So this is for derivative with x1. If we take the derivative with x2, we'll end up with same equation like this. But in that case, we will have mu by m1 and we'll have a minus sign here. You can do it at home. So now if we take the kinetic term, kinetic energy terms, of course in the kinetic energy terms, there will be a minus here, but we just dropped that. So if we write nabla 1 equals like this, given with this equation, and nabla 2 equals from this equation, and we do some algebra, we will have like this one. Here, the capital M equals M1 plus M2 is the total mass of the system. So mu is the reduced mass. So 1 by mu is equals 1 by M1 plus 1 by M2. This is the reduced mass. This value of mu is less than both M1 and M2. And the capital M is the total mass, and that is equal M1 plus M2. Now with this, we have changed the variable, this the kinetic energy terms, from the R1 and R2 dependence to capital R and small r dependence. That is the relative distance and the center of mass position. So we have the Schrodinger equation like this. And also, since R and capital R, they are independent, we can write it like this, okay? The product of two functions. And here, actually R1 minus R2, the distance, the value is equal to the R. So we wrote it as V of R. That is, V depends only the value of R. So we have changed the variable. We have the same Schrodinger equation, but in terms of the relative motion and the center of mass motion. And we have the wave function that is the product of two separate functions. Now, what will be the momentum operators for these coordinates, the small r and capital R? Because we have changed from R1, R2 to these coordinates. Now, we know we have derived these two equations. So, and we know that momentum operator P hat is equal minus IA squared nabla. So, if we use this and we put the operator and we write it in these nablas in terms of momentum, we'll have from here, we'll have P1, the P1 hat equals mu by M2 P plus P. This P is actually the momentum, that is the center of the momentum of the center of mass, that is the total momentum. We will show it, and this P, small p, is the momentum of relative motion, that is the relative momentum. Okay, so we have these two equations. Now we want to solve these two equations to get the capital P and small p. So we have these two, and if we solve it, we have these two equations. So let's do the solutions first. So if we subtract, if we add them, so we have P1, we have P2. If we add them, we will have P1 hat plus P2 hat equal mu by M2 capital P hat plus mu by M1 capital P. Okay, now if we take the sum out, we take the mu out, and we have here M2 plus 1 by M1, we take capital P out, and this is nothing but the 1 by mu. No? We have defined the reduced mass is 1 by mu equals 1 by M1 plus 1 by M2. So this mu and 1 by mu have they cancel out, and we end up with the capital P. So this is the total momentum that we have whenever we add them. So here we again dropped the operator sign, so to write it as a momentum. And to get the other equation, let's multiply both of them. Multiply this one 1 by M1. So we multiply 1 by M1. We have here M1, M2. We have here P by M1. If we multiply this 1 by M2, we'll have here M1, M2. We'll have here M2. Now, if we subtract them from, if we subtract this one from the first one, then we have 1 by M1 P1 minus 1 by M2 P2 equals, this term is same, they cancel out. We have P by M1 minus P by M2. That is, sorry, this will be plus now because this is minus sign. When I subtract, this become, this is, we have 1 by M1 plus 1 by M2 small p, but this is nothing but 1 by mu, so p. Now we can write the small p equals, we multiply this mu here, we will have mu P1 by M1 minus P2 by M2. So this is what actually we have here. Small p equals mu into P1 by M1 minus P2 by M2. The same as here. Now, if we multiply this and do some algebra, we may write it in terms of the total mass also. So here the P is the relative momentum and capital P is the total momentum. Now, so we started with these canonical variables. We have now this other pair of canonical variables. This is a small r and capital R, a small p and capital P. They also satisfy this canonical commutator. we can check with this because we let's take x component for r, capital R. That would be x equals x1 minus x2. And for the p, let's go. Okay, we have here. So for the small p, it would be mu by p1x by m1 minus p2x by m2. So if we take the commutator for this x and p, we have here x1 minus x2. Let's write it like this: mu by m1 p1x minus mu by m2 p2x. Now if we see this x1 do not commute with this p1x, but it commutes with the other one. So we will have like this: x1 mu by m1 p1x, and also this x2 commutes with the p1x, but it doesn't commute with the p2x. So we have here one minus, and we have minus here. This becomes plus. So we have x2 comma mu by m2 p2x. So let's get rid of this to make some space. So I erased mu here also. Now you can see from here we can take mu by m1 out, and this is mu by m1. This will have I h cut, and also here we can take mu by m2 out. This will have I h cut. Now if we take mu I h cut out, we will have 1 by m1 plus 1 by m2, and this is nothing but mu. Sorry, this is nothing but 1 by mu. That means we have I h cut. So they commute. Similarly, it can be shown for the capital R and capital P that they hold the canonical commutation relation. Like here, R and P hold the canonical commutation relation. So we have new variables, new pair of variables, and they also satisfy the commutation, canonical commutation relations. Therefore, we have changed the variables from R1, R2 to capital R small r, and we have the Schrodinger equation in terms of capital R and small r, which we will try to get the solution in the next video. That's all for today. Thank you.